Great, so let's, what we're going to do now is really just run through this understanding the stiffness matrix, strain energy, and eigenvalues, eigenvectors, so that we have a better appreciation for critically interpreting what they are and try to give some physical interpretation to eigenvalues and eigenvectors. That they're not just quantities we compute, but they really have strong physical interpretation and really important from a finite element point of view, really critical that we understand that properly. Okay, so when you consider a bar that is clamped at both the left and the right edge, no loading applied, we're just going to focus now on the global stiffness matrix and see what the effect is when you sort of start clamping stuff. But we're first going to look at what happens to this global stiffness matrix before any constraints are applied to the bar. So we're just going to compute the global stiffness matrix for this problem. So really what matters here is the area and the Young's modulus and the length. That is what we need to be able to compute the global stiffness matrix. So this is before any loads. So the loads are in any case applied as a right-hand side vector, and any of the degrees of freedom are removed. Okay, so the known unknown degrees of freedom are removed. That is important to understand. Okay, so first let's go follow this approach where we solve this with problem with SymPy, so symbols. So we have now symbolic expressions for n1 to n3. We have the isoperimetric formulation. We have the area, and there's a constant area, but we multiply by a 0 and an x just to make sure the type is correct, that it's a symbolic type. We've got E and L. That's essentially what we have there. Okay, so these x1, x2, and x3 are just nodal coordinates. Then we can set up a list of these shape functions. We can divide dx, dy, dx. That's what we can do here. The B matrix is then dy dx times derivative of n with respect to psi, B transpose times E times B. That's essentially our inner core of the stiffness matrix integrand. To complete the stiffness matrix integrand, we need to multiply the area and dx dy, our integration mapping. Okay, so that's what we need to do. But then we can go and say, let's integrate it numerically, and out pops the stiffness matrix. That's what we have. Okay, so if I have this kind of stiffness matrix, its type is SymPy dense, mutable dense matrix. So this is a nasty thing to work with. If I just convert it with NumPy stiffness matrix without specifying the t-type, I will end up with problems later on. Okay, so this is just to make sure that you understand. If I just do this and I work with the stiffness matrix P object and I try to find the determinant of this thing, I run into a problem. So rather specify the d-type. You can do it as a float, or if you want to, you can do it as an np.float or something like that. So there's various ways we can do this, but once we have done this, we can now compute the stiffness matrix. Okay. So that's essentially what that boils down. In some of the SciPys, there might be an issue where you might have to first convert the stiffness matrix to a P object, and then the P object to a float. So it's depending on what version of some SciPy you work with, this might be a bug. So just take note, if this above doesn't work, you first have to then convert this stiffness matrix to a P object without the d-type specified, and then that object we can convert with the d-type float to a float. So that is just, it seems like it's working. This version is working fine on my computer. So this I don't have to worry about, but I'm just putting it in here in case some of you run into trouble. Okay, so stiffness matrix properties. So let's look at the first two properties. The first one is that it's symmetric, and it's symmetric by construction because we used the Lipton-Perlurkin approach. We had the same weighting function form as to the displacement form. So those shape functions we use for the displacement field are the same shape functions we use for the weighting function. That by construction makes it symmetric. And we can see it here again, just as a reminder. When I compute this this integrand, this B transpose of EB, this one B transpose comes from the weighting function. This one B comes from the displacement field, yeah, from the stress. And so this is from that weak form formulation. But this B transpose, I can remember what it comes from. This is the one that came from the weighting function. This one here comes from the stress. That's why we had the E times the B mat, because the B mat was really just the strain. If I multiply by the Q, it's the strain that it represents. So this is the stress contribution, this is the weighting contribution. And if I use the same form for this shape functions for the weighting function as for the strain, then these two beam mats will always be sort of similar. Yeah. And if I take the transpose of the one and then multiply it with the transpose and the thing in the middle is also symmetric, then I always have symmetry. So this is why things are symmetric, because then I just multiply by these scalars afterwards. Okay, so that's important to understand. So that's not just because I'm guessing this is really following just the reasoning through what the algebra is doing. Okay, so this is why this is the case. The stiffness matrix is singular. Oof, what does this mean? Well, what it means is there are some linear dependency in that thing. Okay, so another way of thinking of it is that there are some eigenvectors and some eigenvalues that are zero. It means I can't just solve kq equals to f. If the system is singular, yeah, if a matrix is singular, and I would like to, if I were to use this global stiffness matrix and say kq equals to f, I will not be able to solve it. Okay, it will not solve because it's singular. So what it means is there's not enough, the equations are less than what we think. Okay, and when we think about it from an eigenvalue perspective, let me show you that there are some eigenvalues that are zero of the stiffness matrix. If I go and compute the eigenvalues and eigenvectors with np ln L sort of Eik, I get eigenvalues non-zero, non-zero. Ooh, look at this one, 10 to the minus 9. These ones are 7, 10 to the 7, 10 to the 8. This is our numerical zero value. So this is our eigenvalue, that's zero. So if you look at the columns here, I would like us to see that this is the same value, but this is different. Okay. This and this are different. This is so they're similar values, this is opposite sign, this is different. But this column, this eigenvector, so each column is an eigenvector. This eigenvector has the same values. Exactly the same. This is one associated with the zero there. What does it mean? We're going to see what it means. Okay, so that's important to take note of. We first have to get some interpretations for the stiffness matrix. So first, second aspect that's handy thinking about the world in terms of stiffness matrices and eigenvectors and eigenvalues, is really helps us to interpret what these elements can do. Okay, so and it also helps us to interpret a little bit what they how they contribute towards stiffness. Okay, so first off, we can reconstruct K. This is not, I'm not making this up. I can reconstruct K. This is called the eigenvector decomposition by saying take the eigenvectors outer product. So this is this vector times this vector. This is a column vector times this row vector. The outer product essentially will blow this up to a matrix multiplied by the eigenvalue. So I can write down the stiffness matrix as an eigenvalue times this matrix, eigenvalue times this matrix, eigenvalue times this matrix. And if I add it all together, I can reconstruct K. Beautiful. Look at that. I can reconstruct K fully. Okay, and if I subtract my eigenvector reconstructed K from my original eigenvector of my original stiffness matrix that I computed from the SymPy, I see that the difference is zero. Okay, but now also this allows us to think a little bit about what is the eigenvalues interpretation in this case. If this is the case, and this is the way I can reconstruct the stiffness matrix, then essentially what I can say is this V1 transpose, V2 transpose that are associated with the non-zero eigenvalues are contributing stiffness. And this lambda 3, which is zero, our eigenvalue, is not contributing stiffness. Okay, so there's already, just from looking at this, we can now critically interpret the result and say, this lambda 3, if it's got a zero eigenvalue associated with it, it's not contributing stiffness. So it's contains some information, but it's not related to the stiffness. What can it be related to? Okay, we'll see. Okay, but that is important to understand. And then essentially the V1 transpose, V2 transpose are essentially these unit eigenvectors that blow up to a matrix, and these lambdas are contributing towards stiffnesses. Okay, so they scaling these outer products towards stiffness quantities. Okay, so that is important to understand. And if we look at the definition of an eigenvector, well, the definition is just, it's these special vectors that if I were to multiply it with the matrix K, the direction doesn't change, only its length. That's really what it means. Okay? That's really what it means. And there's a nice interpretation of this if I were to think of it as KQ equals to F, but I don't want to go into that for now. But let's just think about, and I'll leave that comment there for those of you that are interested. But KV equals to lambda V allows us to say these are special vectors, so special vectors that only change. Because normally, if I were to take a vector multiplied by K, it would the directions and everything would change. Magnitudes and directions would change. Okay, so that is important to understand. So if I think about inverses, I can then say let's take inverse on multiply by inverse and multiply by K inverse on both sides, and then I can divide by lambda on both sides, and then I recover this. What it tells me is that essentially the inverse of K, or the K inverse, is essentially can be computed by really just taking 1 over lambda, because KV equals to lambda V was essentially what we had here, yeah, in terms of the normal form of that definition for the eigenvector. And now what I'm seeing here is that K inverse times V is just 1 over lambda times V. So the inverse is really related just to the 1 over the lambdas. Okay, so would the implication then be that if I were to want to compute the inverse of K, I just take 1 over lambda, 1 over lambda, 1 over lambda. Go and check if that's the case or not. Okay, so that's essentially the way the eigenvalues relate towards inverses. Okay, so if I do an eigenvector decomposition, I can then compute the inverse of that K matrix quite easily because of this 1 over lambda relationship. Okay, so that's one aspect that I just wanted to mention there. Okay. And then you can see why there's an issue if I have a 0 eigenvalue. Ooh, can you see that? If I have a 0 eigenvalue, I'm sitting with an inverse that is going to be problematic. If I were one of these things were 1 over lambda, I would run into trouble. If you can see that. So here essentially I'm computing the inverse stiffness matrix, the inverse of it, by taking 1 over the eigenvalues, 1 over the eigenvalues, 1 over the eigenvalues. But this one is essentially 0. Things go crazy. Okay, so that's what singular means. Okay, so that's just to take note. And then the other thing is, another way, we've already spoken about this. I'm going to recap this. This is just an important observation again. K times K inverse equals to I. So this is the definition of the inverse of the matrix. It's this inverse is the special matrix that if I multiply it with the original matrix, I recover identity matrix. That's what it means. Okay, it's got physical meaning. If we relate it back to KQ equals to F, it means I can think of the identity part, the unit column, so columns of the diagonal, zeros everywhere else, as applying unit loads on each of the nodes of the problem, and each of these columns of this inverse is really just the displacement solution. And now we've got a nice way to think about this, and this is something we've done before, so spoken about before. Really important, and this is really essentially when we solve a system for an arbitrary f, we are just taking a linear combination of these unit loads that I applied. It means we're taking a linear combination of essentially this K inverse. So if I were to wanting to compute Q from K inverse equals to I, okay, so KQ equals to F was the system. I could then say Q is equal to K inverse times F. And K inverse is the solutions if I were to apply unit loads to the node. It would have been and then the F here would have now, let's say, a 5 and a 10 and a 15 on some places where I wanted to multiply something. And it will take these displacements and say, multiply it with the multiplication factor away from 1. With the force that you applied there, because what we have is we have the solution for when a force of 1 was applied. That's what the inverse means. Beautiful interpretation of that, really important observation. Okay, so that's that. Again, linear superposition is really the key ingredient to make sure that you follow and appreciate that. Well, okay, but the important thing is, because we work with the physical system, we have physical interpretations of these things. We can really interpret them properly. Okay, another implication of the eigenvectors is that they, in eigenvalues, they form a basis for K. Okay, so if I have put all the eigenvectors and eigenvalues, okay, I have a basis for K, and this is what this demonstrated. Here was K, and I could reconstruct K because V1, V2, V3 form the basis for it. Important observation, yeah? Really important point to take note of. And so what we have is essentially, if that's the case, if V forms a basis, then essentially I could express any of the solutions that I solve from the system. Okay, this Q equals to K inverse F. I could express any of these solutions then as a linear combination of the eigenvectors. That's a really important point, because once I start doing this, I now have physical interpretation of these eigenvectors. Say, oh, they actually mean nodal displacements. Because if I take a linear combination of them with some scaling factor alpha, each one multiplied by some alpha, I just need to figure out what those alphas are. I could express any solution that I generate from this K as a linear combination of the eigenvectors. Stunning, 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 stunning. And that means we're really in a position that we can, 50 minutes. We're really in a position that we can interpret these eigenvectors quite well. Okay, they are now nodal displacements. I'm going to stop here, and then we can continue. I see we're already at 15 minutes.